Hello, my name is Seth Zoppelt, and I research the two-scale factor universality of oxygen, experiments under density gradients. As the critical point of a fluid is reached, there is no distinction between the solid and liquid phase of a fluid. The critical fluids have universal scaling laws that are true for every fluid. We measure the isothermal compressibility and correlation length. When a fluid does approach its critical point, the fluid becomes opaque, as seen in Figure 2, not allowing too much light to pass through it. When an incident light ray is passed through a fluid near its critical point, it will have a different intensity upon transmission through the fluid. Figure 3 shows the light transmission through a sample, and the equation below describes a logarithmic relationship between these intensity values to calculate the turbidity. The hydrogen levitation device, shown in Figure 4, uses a magnetic field up to 10 teslas generated by a cylindrical superconducting coil made of niobium titanium. This coil is dipped in liquid helium at a temperature of 2.16 Kelvin and a pressure of 0.1 megapascals. The experimental cell used is a parallelepipedic cavity of inner length 8 mm made of sapphire and filled with oxygen. The experimental cell is mounted inside a different cryostat, the anti-cryostat, maintained under a vacuum of less than 10 to the minus 7 millibar. Endoscopes for a light source video camera are mounted inside the anti-cryostat. Rather than record light transmission measurements using a traditional laser beam, direct image analysis using a program on MATLAB was used. This method has much potential for space experiments, in particular for DECLIC and the ISS. Critical fluids have many varying applications, including, but not limited to, decaffeination of green coffee using carbon dioxide, dry cleaning of cloth materials using more environmentally friendly compounds, cleaning of machinery parts without use of corrosion-causing solutions, and treatment of tobacco with supercritical carbon dioxide or nitrogen to reduce nicotine content. In particular regards to the space industry and NASA, liquid hydrogen and liquid oxygen are used as fuel for space missions. Gaining a better understanding of the equations that describe liquid hydrogen and liquid oxygen will push forward the search for superior propellants for space missions. A new sampling pattern, shown in Figure 5b, was used to try and incorporate the darker regions of the image and use a broader window to measure the light intensities and turbidities. The intensity and turbidity measurements showed similar results when compared to the original sampling windows, shown in Figure 5a. The pattern shows the transmitted light intensity increasing as the temperature-critical temperature difference increases, and the turbidities decreasing as the temperature-critical temperature difference increases. The images were analyzed in three colors: red at 650 nanometers, green at 500 nanometers, and blue at 450 nanometers. The results for these are shown in Figure 6. A log lin fit was used to analyze the isothermal compressibility and correlation length values. Figures 7a and b show the fittings of the turbidities with the isothermal compressibility and correlation length values. Figure 7c shows the value obtained for the isothermal compressibility, with it represented by the black line. Figure 7d shows the value obtained for the interference term, f of a, shown in the equation below. From these values, we can obtain the correlation length as well. Table 1 shows the final values obtained for the isothermal compressibility, its corresponding critical exponent, and the correlation length. The fitting equations are shown below, showing the relationship between the background turbidity and the critical scaling values. In conclusion, we successfully showed that turbidity data can be obtained using direct image analysis of a fluid under magnetic compensation of gravity. We also found that using different wavelength filters yielded more useful data. The fitting equations for the various parameters are very sensitive, particularly to the refractive index. By fitting the turbidity data to these sensitive equations, we were able to successfully determine our values for the isothermal compressibility and correlation length for oxygen. I would like to thank the South Carolina Space Grant Consortium and the Palmetto Academy for the grant money and the opportunity to do this research. I also want to thank my professor and incredible advisor, Dr. Aprasan.